Okay, now it should work. Michail, you will present yourself or Yorgos will do it?
You can do it, Yorgos can do it.
Dimitri, you do it.
Okay, okay, cool. Okay. Hello, everybody. Thanks for being with us today. Today we have an internal seminar. Our colleague Michail Tsagris, an assistant professor still, but not for long in our department. We'll talk about flexible non-parametric regression models for compositional response data with zeros. This sounds very exciting. Michail, I guess that people can ask you questions during the presentation. Is that correct?
Yes, yes.
Okay, this is cool. Yeah, that's it. So the recording is in progress. The floor is yours. And yeah, people, don't hesitate to interrupt and send questions in the chat. That's it. Michail, the floor is yours. Thanks.
Okay. Thank you, Dimitri. At first, I would like to say that this is a summary of the paper. The co-authors are Connie Stewart from the University of New Brunswick, Canada, and Abdulaziz Al-Enazi from Northern Border University of Saudi Arabia. So, like you said, the talk is about compositional data. So, at first, let's see what is compositional data. So, imagine you have multivariate data where each row sums to the same constant and everything is positive. Well, not strictly positive, in general positive. So I repeat, you have a multivariate data, each row sums to the same component. This component can be, this constant can be anything, but for convenience purposes, we like to take it 1. So the sum of each row sums to 1. It can also be 100, so you can express it as percentages. Now, compositional data arise in many different fields. For example, the most popular applications, we can find them in biology, bioinformatics, geology, geochemistry, but in the last years, we see them a lot in bioinformatics because some type of data are compositional. They sum to a constant. Now, as you can imagine, like most types of data, we can have and have been developed regression models. So we can have covariates. Now, there are 3 types of regression models we can see in the compositional data field. The first one is when the response data is compositional and the covariates are also compositional. Another one is where you have a Euclidean response. When I say Euclidean response, it doesn't have to be truly Euclidean. It can also be a binary response. It can be a multinomial response, a survival response, any type of response, provided that the covariates are compositional. But the focus of this presentation is about the case where you have a compositional response. The response data are compositional, and the predictors are Euclidean. Now, specifically Euclidean, and you will understand later why. I do not allow a mix of Euclidean and categorical predictors, because that case is a bit trickier to address. And I will explain a bit later why. So we focus on, I repeat, on strictly Euclidean predictors, or allow me to correct this, or we can also have unit vectors as predictors, simply because the Euclidean distance in the unit vectors is the classical Euclidean distance. It doesn't change anything. But I prefer to have continuous predictors. Here is an example from geology, just to give you an idea of what happens, and show you an example of compositional data and the Euclidean predictor. The first 3 columns are samples from an Arctic lake, and we measure the composition of the Arctic lake in sand, silt, and clay at different water depths. So the fourth column is the depth of the Arctic Lake. You can see the first, if we take the sum of each row in the first three columns, they sum to 100. But like I said before, 100 or 1 is the same. Now, the idea here is to see how the composition in these three elements, the sand, silt, and clay, changes as we go deeper to the lake. This is a real example, actually. So one idea here is to transform the response compositional data using what's called the log ratio transformation. So the idea is choose one column, any column you like. In this case, I choose the first one. Divide the other columns by the first column, and then take the log of these ratios. Now, from the 3 dimensions, we go to the 2 dimensions. The 2 dimensions are unconstrained. There is no constraint that they sum to 1. And there you can apply the classical multivariate regression with the predictors and the multivariate error components. Now, I repeat, this is the classical multivariate regression problem. We can find this function in the R package compositional. But there is one problem, and I think most of you have already spotted it. We cannot have zeros in the response compositional data because any zero here does not allow to take the logarithm of this ratio. There are ways to perform, let's say, a zero value imputation. When you have a zero, replace it with a very small value and adjust the values of the other components so that the sum still sums to 1. But this has some problems. I'm not going to go through them. So another idea is to, instead of, let's say, minimizing the sum of the squares of the errors in the univariate or the sum of the trace of the cross product of the errors, so instead of ordinary least squares, we can employ the Kullback-Leibler divergence. So we minimize the sum of the Kullback-Leibler divergences between the response, the observed response data and the expected response data. This idea is not actually new. This was studied by Murteira and Ramalho. It was a paper published in the Econometric Reviews. And they used the term multivariate fractional data to denote the compositional data. So in econometrics, we can see them as multivariate fractional data. And they don't say we minimize the Kullback-Leibler divergence. They say we maximize the multinomial logit likelihood. But essentially, a multinomial logit likelihood is minimization of the sum of the Kullback-Leibler divergences. And I prefer this terminology. Now, you will see that the expected response data have this form, which is actually the multivariate logit transformation. This function, to perform the minimization of the Kullback-Leibler divergence, or what I call Kullback-Leibler divergence-based regression, we can find it in this package compositional. And the benefit of this function, in contrast to the OLS function, is that these zeros in the response data are allowed. And you will say, but we have, for example, if we use this function, not this, obviously here we can see that if we have a zero, nothing happens. The function is okay. But if we use this function and you say, but if we have a zero here, 0 log 0, how can we do it? Well, from the de L'Hopital's theorem, we know that the limit of y log y as y goes to 0 is 0. But I prefer this function, maximize this function, because we perform less operations, less matrix operations. So it's a bit faster. What do? We say, let's take the classical k nearest neighbors regression, use the alpha transformation. I don't need to show, I don't want to deviate the talk and tell you what is the alpha transformation, how it relates to the log ratio transformation, all this. But I will explain you in the next slide what do I mean by the alpha k nearest neighbors regression. So what is the idea of the k nearest neighbors regression? At first, we must specify the nearest neighbors. How many nearest neighbors we want in order to predict the response of a new observation x new. Suppose we say we want k, the 10 closest neighbors to my Euclidean predictors. So what do I do there? I will compute the Euclidean distance between this new observation and all my available predictors. Then I will sort the distances. I will take the k shortest distances, and then I will say, what are the corresponding response values of these k nearest neighbors? And I will average those response values. This is the classical way for the k nearest neighbors. But bear in mind one thing. I said we will compute all the distances or the Euclidean distances between this new point and all my available points. This is the naive way to do it. But I will show you later that we do not need to compute all these Euclidean distances for every new point I have, because obviously this would take ages in cases we have millions of observations. But we will attack this problem later. So the second point is, after we compute the closest neighbors, we see the response values of these neighbors and we average them. Well, since we have a multivariate regression, we could, of course, do the same thing. Take the average. But the idea here is, do not take the average, and instead take the fresh mean, which is related to the alpha transformation, but I will repeat myself once again. I don't want to go there. I just want to give you a brief summary of the paper. And I said this in the beginning, this is a brief summary. So I don't want to overload you with extra information, just to take the key message. This is the fresh mean defined for compositional data. The C you see here denotes the closure operation. And when we say closure operation in the compositional data field, we mean you give me a vector and I normalize it by dividing by the sum of the vector values. And then everything sums to 1. This is the idea. What about the alpha? The alpha now is something like the Box-Cox transformation. The alpha can take any values you like, but for convenience purposes, we typically say that the range of values should be from -1 up to 1. But why from -1 up to 1? Well, the idea is simple. If we have alpha equals -1, then this corresponds to the harmonic mean. If we have a value of alpha equals 1, this corresponds to the simple arithmetic mean. If we have a value of 0, this corresponds to the geometric mean. And the idea is here, I will explain this a bit later. I will speak about this geometric mean. So, I repeat, the process is do the classical k nearest neighbor, but for your predictions will come from this fresh mean. So you'll ask now, how do we choose the number of nearest neighbors? How do we choose the value of alpha? Well, the answer is cross-validation, the typical tenfold cross-validation. And the benefit of this fresh mean is that zero values in the response compositional data are allowed, but this comes at a cost. If you have zero values, at least one zero value in your data, the alpha values must be greater than zero, so that the root, let's say, can be defined then. This is the only problem, but other than that, we're okay. Now, there is a paper by Wilfried Kendall, the son of the Kendall correlation, his son, Wilfried Kendall and Willingly, in 2011, and they say that the central limit theorem applies to fresh means defined on manifold value data. Manifold value data, manifold in general, is, let's say, a space which is not Euclidean. And simplex is an example of manifold value data. Now, this Padazis 2019 was supposed to be a citation. This is a mistake. It was a paper we published in 2019 in the Sankia A. And we say that the simplex space is an example of manifold value data.
But can it also be a Euclidean space? Because you said it is not Euclidean.
Yes, the simplex is not
It could be also Euclidean, no?
Sorry?
A manifold could also be defined a Euclidean space.
No. A Euclidean space is a special case of a manifold.
Exactly, yes. I thought you said you cannot have it over a Euclidean space. Okay, I heard wrong. I heard wrong. Sorry.
Okay. So yes, the Euclidean space is an example, is a special case of the manifold. Manifold, for example, is the sphere. The surface of the sphere is a manifold.
Yes. Okay.
So to put it simply, in the Euclidean space, the shortest distance to go from one point to another point is the straight line. So this is a geodesic. In a manifold, our head, imagine the space our head. This is not a manifold, because if you want to go from this here to this here, you don't go straight with a straight line. You have this, you have the nose here, and you can understand. So this is a manifold. So the face is a manifold. Or as I said before, the surface of the sphere is a manifold. You don't go with a straight line, you have a curve. Another nice property of the fresh mean for compositional data, specifically for compositional data and in general, is that it is absolutely continuous as alpha tends to zero. And like I told you before, if alpha goes to zero, we go to the geometric mean. But specifically for compositional data, we will speak of the closed geometric mean, which means a computer geometric mean, component-wise, but this doesn't sum to one. So normalize it. So apply this closure operation. Compute the geometric mean, and then define each element by the sum of the elements. So our fresh mean before, as alpha goes to zero, we end up with a closed geometric mean. But what's the problem here? If you have zeros, alpha, I said before, alpha must be greater than zero. For this purpose, for this reason, you see here. Now, this was for the k-nearest neighbors. We can extend the k-nearest neighbors to the kernel regression. And this is the example of the Nadaraya-Watson estimator, 1962, I think. So what is the kernel regression? Well, in the k-nearest neighbors, you say, I will take the k nearest neighbors and use them. In the kernel regression, you say, I will take all my neighbors, so basically all my sample, but each observation will contribute to the fresh mean with a weight. And the weight decreases as the distance increases, the weight decreases. But in which way? exponentially. In the R package compositional, I have defined two weighting functions. The first is the Gaussian or radial basis function, as it is known in the machine learning field, or the Laplacian kernel. Well, the Laplacian kernel is similar to the Gaussian kernel, but instead of using the Euclidean distance, I'm using the Manhattan distance. And you can see here there is an H parameter or hyperparameter. Well, in statistics, we call it bandwidth, the bandwidth of the kernel. In the machine learning area, they call it the hyperparameter gamma or something. It's a hyperparameter. So we have the same problem as before. How do we choose the value of alpha? And how do we choose the value of h, the bandwidth? The answer, obviously, again, is through the typical tenfold cross-validation. But let me clarify something. We can choose the pair of A and H or A and K using not the tenfold cross-validation, using a repeated cross-validation, using the nested cross-validation. This is, the choice is up to the user. And the benefit of this is that, again, we allow zeros in the response compositional data, but in this case, alpha must be greater than 0. The problem now with this kernel regression is that if we have millions of observations, then we must compute everything. But again, we can attack this problem by saying, instead of computing all the distances, give me, let's say, the 1,000 closest the 1,000 closest neighbors, or the 2,000 nearest neighbors, and apply this weighting scheme in those 2,000 observations. Because after some point, the distance becomes so small, and based on this weighting scheme, the weight will be 0. But to be honest, I don't know what is the limit. Shall I take 2,000? Shall I take 3,000? I don't know. I'm showing you an example here to see how the fresh mean changes when you change the value of alpha. This is a ternary plot used to plot compositional data within the 3 dimensions. I told you before, the sum of the elements sum to 1. So if we have 3 elements, then we can visualize it in the 2D. Because in the 3D we have singularity. And a nice way is to use the ternary diagram. Now, imagine we have here 39 observations. These are the Arctic Lake data I told you before in the beginning. What happens if we take 15 observations? For example, we take 15 observations, not everything, and we compute the fresh mean for a range of values of alpha, ranging from -1 up to 1. The blue is the fresh mean with alpha equals -1. So this is the harmonic mean. The triangle is the fresh mean at alpha 0. So this is the geometric mean. And the black dotted line, point, is the classical arithmetic mean, or the fresh mean at alpha equals 1. You see here that if we have a value of alpha, something below 1, maybe 0.8, 0.9, then if we had the curve, a line passing through those golden points, the fresh mean at that value would be perfect. So this is just an example to see that the alpha in the fresh mean plays a crucial role. And you can understand here the manifold. We don't need a straight line. We have a curved line. And imagine the higher dimensions, the curve becomes a surface. And we need to spot the optimal fresh mean on that surface. Now, let's see a simulation study to see how well the alpha k nearest neighbor and the alpha kernel regression performs in terms of predictive performance compared to the Kullback-Leibler divergence regression. I will not tell you about the OLS, because in this example we have also considered zero values, and it would be unfair to say I compare these flexible regression models with the OLS when you don't have zeros, but only with the KLD when you have zeros. So we decided to compare with the KLD regression, zeros or no zeros. Now, initially we said what happens if you have a linear relationship between the predictors and the compositional data. What happens if you have a second order degree of relationship, when you have a third order degree of relationship, a polynomial relationship, and what happens when you have a segmented relationship, which means, imagine, up to a range of values you have a straight line, and then up to that certain point of values you have a line decreasing. So it's like a segmented regression model. The sample size ranges from 100 values up to 1,000, and the dimensionality of the response compositional data ranges from 3 up to 10 dimensions. And this scenario was performed without zero values and with the addition of zero values. And how do we estimate the predictive performance of our regression models? Well, we will do a 10-fold cross-validation, and we will measure the predictive performance using the Kullback-Leibler divergence. Now, this is a bit of cheating in favor of the Kullback-Leibler divergence regression, because the Kullback-Leibler divergence regression tries to minimize the Kullback-Leibler, and then you say you will evaluate the predictive performance using the Kullback-Leibler. So this is a bit cheating in favor of the KLD regression. Why don't you use the sum of the squares of the residuals? Well, we prefer this divergence because this is more suited for this type of data. And we repeated all these scenarios 100 times and average these 100 Kullback-Leibler divergences and see who is best. In this example, the first row shows the performance of the alpha k nearest neighbors regression in comparison to the KLD regression. The second row shows the performance of the alpha Keller regression in comparison to the KLD regression. The vertical axis is the relative KL divergence. And you can see it goes, let's say, from values from 0 point something up to 1 point something. If you see the curves going above 1, that means the KLD was better. If the lines go below 1, that means the flexible regression models are better than the KLD. And the color of the lines denote the dimensionality of the components. The horizontal axis denotes the sample size. If we check now the first column, we will see that the Kullback-Leibler, the KLD regression, is always better than those non-parametric regression models. But if the relationship between the response data and the Euclidean predictors is not linear anymore, but it's quadratic, cubic, or segmented, the flexible regression models are better. So the answer is simple. If somehow you know that the relationship between your predictors and your compositional data is linear, use the KLD regression model. If it's not linear, use a non-parametric regression model. But in practice, you cannot know that. The same scenario, but this time we have, you don't see, I don't know how to, anyway. This is the same case, but this time we have randomly assigned zero values in the response data. And we see the same thing. The first row, the first column, is when the relationship between the compositional response and the Euclidean predictors is linear. KLD is better. But if the relationship is quadratic, cubic, or segmented, the flexible regression models perform better in terms of predictive performance. Now you will ask me what happens about the inference. I haven't spoken about this, but I will later. Let's see now, before going to real data, let's see what happens with the computational cost. We said before that the k nearest neighbors, you must compute all the distances, and I told you, you don't need to compute all the distances. So let's see an example. We have large sample sizes going from 500,000 up to 10 million. And we want to perform k nearest neighbors regression, and specifically the alpha k nearest neighbors regression. And to make it even harder for our case, I will compute the fresh mean 99 times using 2 nearest neighbors, 3 nearest neighbors, up to 100 nearest neighbors. And I will choose 11 values of alpha. So what does this mean? I will give you the predictions for each value of alpha and for each number of nearest neighbors. So I'm giving you 99 nearest neighbors times 11 values of alpha. So each time I will give you 1,000 predictions for each row. So 1,000 predicted compositional data sets based on 10,000 millions. I want to predict the compositional responses of 1,000 new values. So for each of these 1,000 new values, I will give you back 1,000 predictions, and you can choose what is best. So this is what the alpha k nearest neighbors will do. But the OLS and the KLD will return a single set of predictions. So you can see a single set of predictions. The alpha k nearest neighbors returns 1,000 set of predictions with zeros. Let's forget that we don't have zeros. Let's focus on zeros. I will go straight to the worst case scenario. When you have 10 million observations and seven components in the response variable, the OLS requires 5 seconds. The alpha k nearest neighbors requires 23 seconds. And the KLD regression model, which is based on a Newton-Raphson, so I'm not using Optim or something, an optimizer, I'm using Newton-Raphson, takes 140 seconds. If we go to the case where we have 10 elements in the response data, OLS requires 8 seconds, the alpha k nearest neighbors requires 24 seconds, and I repeat, to give us back 1,000 set of predictions, not a single one, and the KLD requires 300 seconds. Now, I can also tell you that these times, the 24, in about a month, I think in about a month, this 24 will have become 2.4 seconds. Not 24 seconds, 2.4 seconds. Let's see now some real example data. The first case is the GEMAS. We have 2,000 compositional, 2,000 observations, 22 elements, and we have some missing values, but we excluded them. And we also have one vector with a 0. So we have at least a 0. And the second example is the glacial data, where we have 92 observations, and we have only 4 elements. And we have more zero values here. This shows, so we perform the KLD, the alpha K nearest neighbors regression, and the alpha kernel regression, and we want to see the predictive performance. So we must perform this 10-fold cross-validation, tune the values of the alpha and the hyperparameters, and then give us predictions, and then see how good are our predictions. A way to do this, I decided to say, okay, guys, let's, instead of seeing the Kullback labeler, to do something better and see the correlations between each element, observed element, and predicted element. And we can see here that the correlations between the elements using the KLD is the smallest one. The K nearest neighbor and the kernel regression are pretty similar. The same is true if we used the Kullback labeler divergence, but I'm not showing it here. Now, about the glacial, I don't present it here because I'm using it here. I told you before that this whole paper is about predictive performance, because in the machine learning field, we're not interested in how the betas affect the response and so on. But if you ask me, can you tell us something about the X? How does the X affect your compositional data, since you don't have any betas? So for the glacial data, when we have one predictor and 4 elements, or the dimensionality of the response is 4, I'm showing you the non-linear effect of the X on the compositional data. And what does this tell us? Well, as the X values increase, what happens to the compositional data? Well, I repeat, they sum to 1. Well, we see here for the glacial data that the values of these 2 components, the crystalline and everything else, is not affected by the change in the X values. But the values of the red sandstone and the gray sandstone, don't ask me what these are. These are chemical elements I cannot explain. They change in a non-linear way. And you see that this is a bit strange behavior, but in general, as the values of X increase, the red is above the red sandstone values are higher than the gray sandstone values. But after some point, there is a change. The gray sandstone values become higher than the red sandstone values. And this change, the KLD regression cannot capture it. So we have a visualization, I repeat, a visualization of the effect, of the nonlinear effect of a single X value on the compositional data. So to close this presentation, we see that the alpha K nearest neighbor and the kernel regression can improve the predictive performance when we have complex relationship. Secondly, especially the alpha K nearest regression is much faster than the KLD, not faster than the OLS at this moment. I repeat, in about a month, the times I showed you will be at least 10 times faster. I expect they will be 11 or 12 times faster. Why? Because we will take into advantage the power of the KD trees. This from the computer science field. We don't need to compute all the distances. What we want to compute is the distances. Actually, we don't need even to compute the Euclidean distances. What do we want? We have 1,000 values. For each value, I want to find the 100 K nearest neighbors from a database with 100 million observations. And I want the 100 nearest neighbors. How can I do it without even computing the distances, the Euclidean distances or the Manhattan distances? The answer is easy, KD trees. And that will give me, in a fraction of, in centiseconds, it will give me the nearest neighbors without even computing the distances. So anyway, now the benefit of the kernel regression compared to the k-nearest regressions is that it provides more flexibility. You have a weighting scheme, but at the cost of being computationally more expensive. And like I said in the ultimate slide, we cannot afford statistical inference, but we can visualize the effect of the covariates on the change of the compositional responses. And here are the references. So I think I will stop here and give space to questions.
Okay, thank you, Michail, for the very interesting presentation. People from the audience, please don't hesitate to ask whatever you like, make comments. The floor is yours. Yes, Grigory.
Hello. A quick question, maybe I have missed that part. How do your results in terms of predicting performance, because you said you're interested in predictive performance, compared to a Dirichlet regression, for example? Did I miss something? Did you mention the Dirichlet regression?
No, I didn't mention it. The Dirichlet regression would give us similar predictive performance to the OLS and the KLD. These are similar because both the OLS, the Dirichlet, and the KLD, they have the same multivariate logit link function. They use this function. So the results are not that different when you don't have zeros, of course. But the reason I didn't do Dirichlet regression is because it's very slow. At least I don't have a fast algorithm, to perform Dirichlet regression.
But Dirichlet can deal with zero values, 0 percentages, right?
No. Dirichlet cannot deal with zero values because you have the log of y. In the log likelihood, you have the phi times log of y. In that case, you need to use the zero adjusted Dirichlet regression or inflated zero Dirichlet regression. That can deal with zeros, but that is much slower than the classical Dirichlet regression. And that's why I didn't use it here. But again, the results wouldn't be that different from the KLD regression.
Okay. Thank you.
Thank you, Grigory. Somebody else? Questions, comments?
Maybe I can make a comment, Michalis Tikanis. I'm Michail Greenacre.
Oh, hello, Professor.
Nice to see you, and thanks for giving us these links for the talk. So it was very interesting. Thank you very much. I just want to make a comment about that last graph you showed us, because the very last one, just before the concluding ones. This one, yeah. Now you ignore those two very rare components, saying they're not changing very much, and you concentrate on these the two upper ones. But we know it's the relative values that are important. So those could be actually changing quite a lot, those two lower ones. So it's just a problem with the scale. The vertical scale should show, for instance, a log scale would be better to see the changes in the crystalline and the miscellaneous components.
Well, if we take the sum for each value of x, these are compositional data. They sum to 1.
Sure.
So the value of this, plus this, they still sum to 1.
Sure. So I'm saying that the rare ones could be changing in a relative sense quite strongly.
Yes, I see. So yes, I understand. Yes, yes.
But you don't see it because of the vertical scale here.
I didn't thought of that, to be honest. Yes, but now I understand. And I think this was a comment made by a reviewer. I hadn't understood it that time. Yes, I see what you mean. Yes.
So just a log scale would show it better.
Yes, you're right. But there is an obstacle. If we have zeros, we won't be able to see the log.
Sure. Okay. Thanks very much.
Okay, thank you. Thank you for the question.
Thank you. Somebody else, perhaps? Comments, questions? Or perhaps, Michail, the main takeaway, what an economist like me can learn from this in one line?
Well, the economist, if you are interested in predictions, let's say in predictions of the percentage of the allocation of the household income allocation in the expenditures, you could use this. But if you want only that, if you are interested in the predictability, in the predictions.
I see.
Just that.
No, but that's pretty clear. Thanks.
Yes.
Somebody else from the audience? Comments, questions? Frankly, I don't see anybody in the chat or any raised hands, so I guess we can wrap it up. I remind you that the recording will be available in our YouTube channel, so don't hesitate to take a look and get back to Michalis with comments, questions when this is posted. Michail, thank you for the very interesting presentation. Again, people in the audience, thank you for attending this seminar. Please don't hesitate to attend other seminars that we have in the future, and also check the collection of videos that we have in our YouTube channel. If there are no more comments and questions, let's close it here. Okay, thanks again, Michail.